Hello. So welcome to our lecture on the EM algorithm. So just to figure out where we are in the flow, because we kind of have this flow of looking through a bunch of these unsupervised algorithms. We kind of got our hands dirty with k-means and GMM. These were our first two unsupervised algorithms. And what we're going to try and do is kind of generalize what happened there so that we can use it in many different settings and move on from there. So last time we saw these two algorithms, k-means and GMM. If you don't remember, the GMM algorithm was the one that we had these photons that we were trying to fit Gaussians to, maybe 3 Gaussians that look like that. Don't worry about if you don't remember the details, just roughly what we're dealing with. And the big idea we encountered was this idea of a latent variable. And the latent variable in this setting, if you remember, was this fraction of points that come from a source. So we didn't know how many points were coming from each one of those light sources that were out there. We had to estimate that. Once we estimated that, then we would be able to go back and fit all the different parameters that are there. Okay. Awesome. So, and the fraction of points, we also had to figure out the linkage, the probability that every source was coming from a point. And then we could do the estimation. And the main thing that I wanted you to take from both k-means and GMM was this main idea that we kind of guess the latent variable. I think this is a great way to put it, and kind of how we have in the notes. You guess where they're probabilistically linked. That is, what's the probability these points belong to cluster 1, this point belongs to cluster 2, so on. And then once you have that, you then solve some estimation problem that looks like a traditional supervised learning. So that decomposition is quite important, and we're going to try and kind of abstract that away. And then we would estimate the other parameters. That's what I mean by a kind of traditional supervised thing. Now today, what we're going to do is we're going to take a tour of EM in latent variable models and try and cast them on a little bit more principled footing, because last time the calculations were, yeah, it kind of makes sense that that's the average, the weights in a cluster. We'll try to derive the action that we're doing there from a more principled framework, which is MLE. Doesn't mean that it's right. Maximal likelihood is just a framework. It happens to be, though, the framework that we use throughout most of the class. There are others in machine learning, by the way, but this is the one we're going to use. So before I get started on kind of the rundown, any questions there? I'll start to write. Oop. Oh, please.
Yeah, for k-means, we start by casting the views.
Right.
What is the first step in GMM? What do we guess?
We could guess randomly an assignment of every point to the cluster, the probability. Remember there was this Zij. If you don't recall, we'll bring that up later. Don't worry about now. But we had to guess for every point xi, which of the k clusters it belonged to and with what probability. We could, for example, initialize that to uniform. We don't know anything, right? And that's something. We may have some other heuristic guess. That was what was going on in the k-means plus. We may have a smarter initialization. But that's how we get the process started. Once the process is started, we just keep running those two loops again and again, and hopefully it will improve. And we'll capture in what sense it improves. You'll see this weird picture of a curve that we go up, and that's going to be the loss function. Awesome. Okay, so we're going to look at the EM for latent variable algorithms, and this is where it applies. This is what it's for, is dealing with various different notions of latent variables. And I'll say this right now, maybe a little bit cryptic, and I'll come back to it either at the end of today's lecture or in the next lecture. When we pick these latent variables, there's kind of a little bit of an art. What they're doing basically is they have that decoupling property. If we knew this thing that we couldn't have observed, then all of a sudden it becomes a really standard statistical estimation problem. And somehow we're assuming structure, and that's what we're putting into the latent variable. So we're going to see, walking through this today, that structure, we're assuming there's this probabilistic map out there that says how often, how likely every point is to go to every cluster. In other cases, we'll see more sophisticated variants of this idea, but it's actually fairly profound. That's the real key idea. We can abstract all the algorithmic details into EM, same way we did for the exponential family stuff. Okay? Now, before we get started, I want to take a technical detour, and so it's really important that we have signposting here, because they'll say, why is this guy drawing these weird pictures? The technical detour is I want to make sure that you understand this key result, which is convexity and Jensens inequality. And the reason is I'll refer to this thing as we go through. We're going to use it. It's not like I'm just teaching you something for your health. Like this is actually going to be used in the next step. It will actually, in some sense, be the entire algorithm. Like if you understand this in the simplest way, then understanding the algorithm will make a lot of sense. It'll become a clear point where we apply Jensens inequality, where we make it tight. Those are the things that we're going to think about as we go through it, okay? So we're going to do this technical detour, and I'm going to try and show it to you in pictures because I think it's the most intuitive way to understand kind of the basic cases. If you already know it, don't worry. It's just another proof that you'll see. Then this will allow us to go to doing the EM algorithm as MLE. And what I mean is we're going to be able to write down a formal loss function, a likelihood function, right? That's what MLE is. We write down this loss function, and then we maximize the likelihood. And we're going to show that this actual algorithm is actually under the covers maximizing a likelihood function, all right? Then I'm going to come back and I'm going to put GMM into this framework. And this will answer some of the questions that we kind of intuitively, kind of heuristically answered, like why are we estimating those parameters in such a way? And that will allow us to say, yep, GMM is an EM algorithm, and so it would give us a principle to solve for all the weights. If you remember, there was those cluster centers, the mu's and the sigmas, the source centers, mu's and sigmas and fractions, and we were going to solve for all of those. And this gives us a principal way to do it because we're in this MLE framework. Okay, so we'll exercise it, basically exercise the notation. And then we almost certainly will not have time for this today, but I combined the notes, and we'll go through continue to go through them on Wednesday. We'll go through what we call factor analysis. Okay, and factor analysis is another model. The reason I want to show it to you is it's different than GMMs, so it occupies a different space, and it will kind of force you to look at the kind of decisions you're making, right? What are you modeling here? And in particular, we'll model a situation where like traditional Gaussians kind of couldn't fit the bill because we're modeling something that's huge and high dimensional, and we have to assume some structure to be able to get the whole program to work. And by comparing these two and what's similar to them, hopefully you get a pretty good sense of what EM is and all the different places that it runs. Okay. All right. Okay, so far so good. So if there are no questions, we're going to go right into our technical detour, which will lead then into the EM algorithm as MLE. Okay. All right. Okay, so here's our detour. This is convexity and Jensens. So this is a classical inequality, and what I want to show you is that Jensens inequality really is like convexity in another guise. Okay? And it's a key result, so I want to go slowly. That's the only reason we're doing this. Okay? So don't think that there's something super mysterious going on. There isn't. Hopefully, if I do my job well, you'll just look at the pictures and be like, oh yeah, that makes sense. Okay? Here's the line. I see what's going on. Okay, so first we're going to define a set as convex. And we did this last time, but just recall. A set is convex if for any A and B element of omega, set omega, sorry. For any, the line between them is in omega. So I'll write this in math so it's precise. Is in omega, okay? So what does that mean? So let's draw the picture first and we'll draw the math. Here's the convex set. So it means no matter how I pick A, here's A, and no matter how I pick B, the straight line between them, the geodesic between them, the straight line, is in a set. This is convex. Okay? In contrast, just to see this is not a trivial definition, this thing here, which I drew very crappily, but that's okay. I'll draw it like this, because you'll see why the bottom makes more sense to me in a second. Here, we have one example. So if I picked A here and I picked B here, yep, the line is in the set, but that doesn't prove it's convex. It has to be convex for all of the choices. And here, if I put it for B, lo and behold, this would not be convex. Okay, so let me write the math while I have the picture. So this is in symbols for all lambda, element of 0, 1. So this is how I'm parameterized going on the line. AB element of omega, lambda A plus 1 minus lambda, accidental stroke, lambda B is an element of omega. Okay, clear enough what that means? This is just the line between A and B, right? I'm just saying that no matter how I pick A and B and lambda, this thing still remains in the set, which is just capturing this picture. Cool. All right. Now, we're going to apply this to functions. So given a function, for right now, we make it one-dimensional, GF. We're going to define the graph of that function as a set of xy such that y is greater than f of x. Okay? Okay, this is my definition. So a function is going to be convex if its graph is. Okay, as a set. Okay, so let's draw an example of this. So here's my function. Here's 0, here's -1, here's 1, and I draw this character. Okay, so this. Okay, so the shaded region here, so this function, by the way, the one that's in my head, is going to be f is equal to x squared. So if you're trying to correct for my artistic shortcomings, this is f equals x squared. It's a parabola, kind of a bowl-shaped function. All right? Now, no matter how I pick the points, and clearly I should really only have to worry about picking them on the edge. So if I pick a point here, A, and I pick a point f of A, I pick a point B, and I pick a point f of B, the line between them, right, goes here. Right? It's not necessarily a straight line across. I just happen to pick it that way. Go up, it go down, do whatever it wants. Okay? Now this function here, we'll talk about a point z later. So I'll just say there's like a point z that's going to live in the middle. Okay, and this is b, lives here. Let me erase 0 and 1 because we don't really need them. Their values are kind of unimportant to us. This is just so you knew what I was drawing. Okay, I'll draw A. All right, awesome. All right, now what is this function? Well, this is, I think it's x minus 1, x minus 2 squared. Looks like this. And then its graph is everything up here. And this is not convex for the same reason. I could pick a point here, I pick A here, I pick B here, and the line between them is below the set. So this is a convex function. This is not convex. Okay, so let's look at this in symbols. So clear enough? Hopefully like trivial, like, oh, you just drew two pictures twice, and one you said was a function graph and the other one you didn't. The function graph was open to the top, but that shouldn't be really disturbing. So far, so good. All right, so what does this mean? It means for all lambda element of 0, 1, lambda a f of a plus 1 minus lambda, these are as tuples, b f of b, is an element of omega. What does it mean to be an element of omega? It means that if I take any z that's on the path, lambda a, to 1 minus lambda b, so any character that comes in between here and here, then it had better be the case that lambda f of a plus 1 minus lambda f of b is greater than f of z. Right? So this is now z, f of z, this is z, this is f of z. Does that make sense? Just translating the definitions directly. In more cryptic language, we usually just tell you every chord is below the function. Oh, sorry, it's above the function. Sorry, I'm drawing the wrong way. Above the function. What does that mean? Well, a chord is just anything that connects 2 points here. So like this character would be another chord. It lies entirely above the graph of the function, where the function actually lives. Here, that's not the case. I just found 2 points so that the chord between them is actually below the function. So it's not convex. And intuitively, the reason I drew these shapes is that convexity for shapes probably makes more intuitive sense, 2D shapes. But now hopefully you see they're really the same thing. So your geometric intuition and the function intuition are the same, modulo that we change this definition here. Okay? All right. Now, let me see. All right. So one other bit here. So we'll actually prove this, I think. Why not? Sounds like a fun thing to prove. If f is twice differentiable, and for all x, f double prime of x is greater than 0, then f is convex. Okay? So this says these functions really are bowl-shaped, right? Second derivative being positive means that they have this kind of positive curvature that looks like the u's, right? Their first dimension, the first derivative goes up and down, but they're kind of always trending. The first derivative is always getting more positive, right? It's negative on the left-hand side, positive on the right-hand side. That's what it means by bowl-shaped. Okay, so this isn't super hard to prove, but just because I think it'll stall for a little bit in case you want to ask me questions. I'm writing out the Taylor series for this. F double prime, zeta A minus Z square. Okay, plus. Let me drag that guy so it's a little clearer. Okay, and this A to A is just something in AB. So maybe you remember this from your Taylor series. All I'm saying is I can write f of A as some point f of z plus some first derivative information plus some second derivative information, and then I'm using the second derivative of remainder. So I'm saying there's some point on the interval where this is true. Okay? Same thing for B. This isn't super important for your conceptual understanding, by the way. Like, this is just to show that you can do what you want to do here. That this makes sense to you. B minus C squared lambda B. Okay? Now I claim it's convex, so I just take what's the obvious thing to do. I'm going to multiply this by lambda. I'm going to multiply this by 1 plus lambda, so that I have to make a statement about this. Right? That's what's in my definition above. Okay? Well, that's just the same as adding f of z for lambda plus 1 minus lambda. That's just f of z. So that's good. That appears. Notice here that I get 1 plus a times lambda plus 1 minus lambda times b. Well, that's just equal to z exactly, right? So I get 0 here plus 0, right? This is just because lambda a plus 1 minus lambda b equals z. Plus, these things are all positive. Plus some constant that's greater than 0. So that shows that this thing, this inequality holds, f of z. Please.
So in the F double prime, is that A top? Like
Yeah, this is Taylor's theorem. Great question. So what's going on here, if you remember Taylor's theorem, is you can keep expanding, and then you have the last term, which is the remainder term. And the remainder term says there exists some point that lives in A to B such that this holds with equality. And I'm just using the remainder form of Taylor's theorem. By the way, if this is really not important for your conceptual understanding, I just want to show that it's one line, that this statement, which is like sometimes mysterious about derivatives and causes people's heads to explode, like why do the derivatives connected to the convexity? It's like because of this. This is all that's going on. Awesome. You can freely forget this and just use this fact in the course. Okay? Okay. Stalling done. Any more questions? Awesome. The real reason we want to go through the derivative thing is otherwise this thing which we actually do care about is strongly convex. This definition feels like it comes from space aliens otherwise. If on a domain is if f prime of x is greater than 0. Strictly greater than 0. This is strict equality here. Okay? That's where the strongly convex comes from. Or this is actually strictly convex. Doesn't really matter. But. Okay, so for example, f of x equals x squared, which I told you was in my head. Well, this gives me a simple test, right? Its second derivative is 2. That's greater than 0. It is the prototypical strongly convex function. Okay? You also saw those 1/2s floating around. This is to make this parameter sometimes with the curvature 1. Doesn't really matter. Okay? The other function that I had, which you can check and graph yourself, is x squared, x minus 1 squared. This is not convex. Compute the derivatives, you'll see, but it's the one that looks like the 2 bumps. Right? It's a quartic, so that's what it looks like. It has 2 bumps. Positive discriminant. Okay? Awesome. So at this point, what do I care that you know? Not too much, honestly, about this. What I care that you know is that there's some way that you are familiar with geometrically what convexity means. And you know that there are these tests in terms of the derivative. The second derivative being non-negative is a good test for convexity. And if you have a stronger condition, you can get this strong or strict convexity. Okay? All good. All right. Now, what we actually need. Jensens inequality. Now, if I've done my job well, this mysterious looking statement, once I show you the connection, you go, oh, okay, that makes sense. It's because it's actually just saying something about convexity, but it's got a fancy name, and it's so useful. And it's the following statement. The expected value of f of x is greater than f of the expected value of x, so long as f is convex. Okay? Why the heck would this happen? Let's take one example. Suppose x takes value a with prob, I don't know, lambda. And x takes value b with prob 1 minus lambda. Then what is this saying? It's saying the expected value of f of x is equal to lambda times f of a plus 1 minus lambda f of b. What is f of the expected value of x? Well, it's f of lambda a plus 1 minus lambda b. That's exactly the definition of convex, the inequality. This is convexity. Okay? Now, one thing that is the other thing I want to say for this is, notice that this does not matter how I pick lambda. Later, I'm going to define a curve. When I define a curve. And that curve is going to be as a result of sweeping some parameters in a high-dimensional weird space. But basically, it says no matter how I pick the parameters of that curve, anywhere that lives on this thing that's a probability distribution, a bunch of numbers that sum to 1 in the discrete case, this inequality holds. And that's going to allow me to build a lower bound for my function, and I'm going to hill climb using it. We'll see that in just a minute. That will become clear. Are there any questions about this piece here? All right. Now, you may look and say, okay, well, this is only in the case when there are 2 probabilities. What happens when there are more? You can just repeat by induction. You have to do something fancier if you want something that's a full probability distribution. This holds even if E is a continuous distribution. I won't show you that because we're not going to go too far off. We'll stop at, kind of high school calculus. Sound good? All right. All right. So now you know Jensens' theorem. And hopefully, you'll always get the inequality the right way. And the reason you'll always get the inequality the right way is you'll draw the picture of the function and see the chord's always above it. Which one must be z? Which one must be f of z? F of z must be below the chord of the function. And that's exactly this. Cool. All right. Now, everything is defined in the literature traditionally for convex. If you take convex analysis, like it's the way we define things. We actually don't want to use a convex function here because we're maximizing likelihood. And this is just notational pain, right? Like if we were, maybe we should have minimized unlikelihood. I don't know what we should have done. But this is where we are. So we need concave functions. And what are concave functions? G is concave if and only if minus G is convex. Right? So we flip it upside down. Okay? The prototypical one that we'll use, if g of x, for example, is equal to log of x, here's my picture of log of x, probably not very good, is that's going to look something like this. Go off this way. And notice that if I take a chord of this function, right, that's a chord, it's below, chord is below, right, which is what I should hope, right? If I flipped it upside down, the chord would be above. Cool. Now, also, there are functions that are concave and convex, right? So what if h of x is equal to a times x plus b? It's a line. Chords are both no longer above and below. It's actually concave and convex. Linear functions are concave and convex. Okay, that ends the detour. Let's get back to machine learning. Okay? So now we have the tools just to make sure what did I care that you got there. You got this way that as long as we were dealing with probability distributions, no matter which probability distribution we took, we have this inequality. We can get lower bounds. We're going to use that in a second to draw some curves of a likelihood function that will hopefully be easier to optimize than the original function. And we'll try an iterative algorithm that will look exactly like we talked about before. And the way we'll conceptualize it is we solve for some hidden parameter. We solve and that gives us an entire family of possible solutions. We solve on that and we iterate. Let me draw the picture after I give you the formal setup. Okay. Oops. All right. So EM algorithm has max likelihood. Has max likelihood. I'm just going to put MLE. All right. So remember, this is the max likelihood formulation. There's some theta that lives out there. We have some data, I from 1 to n. These are our data points. We take a log of the probability that we assign to the data given our parameters. So this is a way for us to compare different parameters, right? And recall, these are the parameters, params, and this is the data. So far, so good? All right? Now, we're working with latent variable models. So latent variable models mean that P has a little bit of extra structure. Px theta, this is a generic term, right? This is just one of the I terms. It says the function factors this way. Looks like a sum over z, where z is our hidden or latent variable, Pxz theta. This is a latent variable, right? So remember, z was our GMM latent variable, the cluster probability, right? So we have to sum or marginalize over all the possible choices of z. This is basically saying, I don't know what z is. I have some probability distribution that I can compute over my data and z given theta. And since I don't know what z is, the term is I marginalize it out. It means I sum over all the possible values. And this will get me back a probability for x, right? This is a sum over all possible z's. This will leave me with a probability for x, probability for x. Is that clear? Yeah, ask a question, please.
So where is this z coming from again? Like, is that a property of the parameter? Like, what is
Yeah, wonderful question. It's a property of the model. In a real sense, when we make a modeling decision and we say there exists some structure out there, like there exists a probabilistic assignment between photons and point sources. One version of the prior is I tell you exactly where every photon comes from. That's clearly a very strong prior. If you knew that, Godspeed, go do it. You just solved GDA. If instead what you know is there exists some mapping that's out there, then that's structure that you're putting into your function. And what I'm saying is that mathematically comes down to baking exactly this in. Okay? And this is the mathematical form for all of those latent variable models. So when we have that idea about latent structure, we'll eventually put it into this mathematical form. And we'll see a couple more examples. Wonderful question. In GMM, this was exactly the z there. The notation isn't an accident. It's the same z. Go ahead.
example of like this?
Yeah, so the example that we had was basically the whole lecture where z was the probabilistic linking between sources and photons. Yeah, so that's one. We'll have more examples later, but I want to get through the algorithm in this abstract form, and we can shoehorn more things into it. And what I'll do afterwards is put GMM right down in this language. We need a couple more things. Please.
Correct me if I'm not understanding this correctly, but so if z is the probability that a point is coming from a particular cluster, what is probability of x parameterized by theta actually represent in this case, in that photon example?
Yeah, exactly. So remember, I think it was said yesterday by someone here on that side of the room. So I don't know if that spatial recognition helps you in the last lecture, but it was like, imagine I was guessing all the photon models that were out there. So each one was parameterized by some choice of zi, and then what I'm thinking about is what I want over that is that across all those thetas, no matter how I instantiate z, each one gives me a different probability distribution. I can sum them up. And that tells me, given this theta, no matter how z is assigned or marginalizing across all ways that it's assigned, how likely is the data? So px theta we've been using forever. We use that from the supervised days. We just inserted z and said well, there's this wild z that we can't observe, but it somehow constrains x. It means that x, the relationship between theta and x. And that's what the model does. Awesome question. Very cool. These are wonderful questions. I'd much rather answer these than badly draw the pictures that come next. We're going to get to those pictures no matter what, so there's really no saving us. All right, let's get to the bad pictures. All right, so I'll try and leave this more or less on the screen. here's the algorithm. This is a picture, which maybe won't make perfect sense to start with, but we'll get there. Algo. All right, so remember what a loss function looks like. I'm drawing everything in 2D, but of course this is in like horrible high dimensions. This is, my axis is theta. And then what I have, and I apologize, I will use a bunch of colors. I hope this is okay for people to see. If not, let me know. It doesn't look like the most visible color, but doesn't look like the least visible, and I need a couple. This is my loss function L theta, okay? So this is, I'll write that in black there. This is L theta, okay? So this is my loss curve, okay? This is L theta here. Now remember, it's not a nice concave or convex function, right? We wouldn't expect it to be. We would hope, because we're gonna minimize it, that it's concave. That would be nice. If it just looked like this, like, oh, that'd be so great. We would just climb to the top. But we saw in a lot of the problems that we were after, it doesn't look like that. It has these kind of weird bends. So we had to settle, that's another way of copying out and saying we had to settle for these local iterative solutions. That's all we're after. We settled for that in KMM, in k-means, and we're gonna settle for that in GMM, okay? So how does the algorithm work? We start with an initial guess. Now again, you could ask, these colors seem harder to read. You start with an initial guess. So theta, let's say at time t. So it could be time 0, right? This is just the initial guess, whatever it is. Then what happens is, this is mapped up to here, which is L of theta t. I haven't written anything, I'm just giving notation. This is just the value of the loss that I currently have. I suspect there's something up this way I'd like to get. So how do I do it? What's the algorithmic piece? What I'm gonna do is I'm gonna form, so the problem is optimizing over all those z's seems daunting, directly optimizing the L's. So instead what I'm gonna do is I'm gonna come up with a local curve, okay? And I'm gonna call this curve Lt of theta. It's another function. I'm only drawing a piece of it, but it goes the whole distance, right? It's some curve. Now we'll pick Lt usually to be some nice kind of convex function, something that's easy to optimize, right? So we're gonna try and get that kind of easy to optimize function. And then what we're gonna do is we're gonna optimize that function. We're gonna find its local maximum. So its local maximum, for the sake of writing, is, let's say, here. And then we're gonna set that to be theta t plus 1, okay? And this is now L of theta t plus 1. And we're gonna, again, create some new curve, Lt plus 1 of theta, based on that point, okay? And the key aspects of the point that I'll write in a second is, this point is a lower bound, this curve is a lower bound, it's always below the loss. So it's kind of a surrogate that I'm not overestimating my progress. And it's tight. It meets at exactly that point. So if I did happen to have the actual optimal value, it would meet at that point. So I wouldn't think and get fooled that there was a higher loss function somewhere else. Let me write those two things, okay? So first, Lt of theta is going to be less than L theta. We'll call this the lower bound property. Lt of theta t is going to be equal to L of theta t. We sometimes call this the tight property. Okay? Our hope is Lt is easier to optimize than L. So this picture, the content is, we're picking these, like, that was a really bad drawing of one, but picking these concave kinds of functions, which are easy to maximize, right? That's what I mean by it kind of looks like a supervised thing. Then we maximize that, and this is formalizing the back and forth. We take that new maximum that we have, which is our new best effort of parameters, and then we then do it again and create another curve. Now the way we're going to create that curve, you're going to see in 1 minute, it's going to be Jensens, and that's the whole algorithm. Okay? So I'll sketch the algorithm. You don't have math to talk about the algorithm, but hopefully it's clear like what's going on. Easy to train surrogate, and we kind of slowly hill climb with that easy to train surrogate, alternating back and forth. And this is what we were doing in k-means. This is what we were doing in GMMs as well. And just so it's super clear, I want to make clear here, phi t plus 1. This is nothing more than the arg max over theta of Lt of theta. Means I do the optimization on the surrogate curve that I created. Cool. All right. I think that this description hopefully gives you some intuition of what's going on, because otherwise the math is kind of bizarre looking. But we'll see. So this is the rough algo. I'm just restating what's on the thing. I'm not giving you enough math. This is going to be called, not surprisingly, the E step. And this says, given 5t, find this curve, L of t. And then the M step, and together are EM, given L of t, set phi t plus 1 equal to argmax phi LT phi. Cool. Please.
That's good. Like, why are we not doing gradient descent on the original turbine?
Right. So we could imagine doing some kind of gradient descent here, but it's not clear how to deal with this marginalization that happens in the middle. So if we did like some marginalization or some sampling, we could do something that looked like that, but it's because we have this decomposition. We also know you can also imagine that we have like a decent solver for the inner loop because it's this nice to solve thing. I would say over time, this split of like what's nice to solve and what's not, right now I'm pitching it as, kind of to you as like, it must be concave and so it's nice, but this kind of just means like I have an internal solver that's like fast and I kind of trust, and I have something on the outside that's a latent variable that I'm like splitting up the modeling. It's one of a number of decomposition strategies. Doesn't mean it's the only way to solve it though. Wonderful question. Cool. All right. So the question is, how do we construct L of t? And I claim we know everything else. So we'll come back to that claim in a second. Okay, so let's look, it's going to go term by term. So let's look at a single term in our equation. Okay, all right, so I'm going to grab one of these characters, just one, and work with that. Okay, so how do we construct it? So right now we're trying to understand how to create this L of t from this function. And you should roughly be thinking, because I told you, that Jensens will have something to do with this, okay? Now, what we're going to do to put it in the form where Jensens could be used looks wholly unmotivated, okay? Totally unmotivated, but it's to shoehorn into what we're doing. And there's some motivation, but it's kind of opaque, so let's see. What I'm going to do is something which at first glance seems strange. Now, this is true, formally, for any QZ that I pick. Okay, please. Oh, sure. So here, I'm just introducing Q. This is true for any Q, right? Let's not worry about support issues, but like, I'm just putting in something that divides by 1. Seems sort of unmotivated to do this. Now, I'm going to only consider, we get to pick Q, so I'm going to pick Qs so that I can use Jensen such that it's a probability distribution over the states, such that the sum over QZ equals 1, and QZ is greater than or equal to 0. Okay, and I'm going to call this property star. Okay, so I'm going to pick Q as a probability distribution. I'll write that in a different color. Okay, why? Because now I can make my argument one line. That's the real reason. So how does it work? Well, okay, good. So we have this character, copy, and here. This can also be written, oops, I don't want to use blue. This can also be written as an expected value where Z is distributed like Q, right? Of this weird looking quantity. Why is that? Well, it's just the definition of expectation. This is just symbol pushing. There's nothing deep going on. But it's important symbol pushing because it means Jensens applies. Oops. Log of this thing, sorry. Damn it, I forgot a log. Okay, I'm just transforming this thing internally into this notation. Yeah, please. Q is this function that we picked up here. So Q is just some probability distribution. And this is going to define our curve, getting a little bit ahead of ourselves. We're going to allow, the curve is going to be parameterized by whatever probability distribution we want. So it's our degree of freedom. I'm just telling you something that's going to hold no matter how I select the probability distribution. The tool that I have in my arsenal to do that is Jensens inequality. Now I've turned this into an expectation, and in one line I'm going to be able to turn it into a lower bound that works no matter how I pick it up. Graphically, what I'm doing, sorry to confuse folks who are copying, is basically show how to construct this LT that's always a lower bound everywhere. And that's where I'm going to use Jensens inequality. So let's see that next line. We'll come back to this. So this is less than, I can pull the expectation out. P xz theta over qz. This is Jensen. Okay? Log is concave. This is equal to sum qz times log pxz theta qz. Again, just symbol pushing. Okay, so there's only one content line here. Okay? The key holds for any q satisfying star. Okay? Okay? No matter how I pick the probability distribution, this chain of reasoning goes through. Please.
Yeah, can you explain how in the first, the second line, like how did you convert the log of that thing into suddenly the expectation?
Yeah, so this was exactly Jensens inequality. So if I scroll back up, this was Jensens inequality, but because I was applying it to the negative of it, it's exactly the same piece, right? It reverses the inequality. And so I'm directly applying that reasoning.
I mean, like before that, like how do you convert?
Oh, this thing into this thing?
Yeah.
Yeah, sorry. So this is just because Q of Z is a discrete distribution, and the definition of expectation is this is a bunch of numbers that sum to 1. So this is an expectation with respect to some distribution, in particular the one where Zi occurs with probability Q of Z. Zi. That's it. It's, again, just symbol pushing. Please.
The distribution of Z is according to phi, where phi1 plus phi 2 equals 1.
Yeah, so you want to know how we ground it into an example. Is that what you're asking?
Isn't phi contained in the theta?
No, so there's no phi here. So apologies if there's something difficult to read. There's a theta here. There's this new Q that I've introduced. Q is something that I've artificially introduced. And I'm just saying that, like, I've just proved, all I've shown here is that I have a way of, if you pick a Q that satisfies this, I have a way of lower bounding this function, getting a family of lower bounds to it. And I'm trying to give you the intuition of why I might want to do it. It's so that I can construct those curves that come later. Because now this function is going to be much nicer to optimize. But we haven't quite gotten there yet. Awesome. Okay? So this whole thing is, this gives a family. This is just what I was saying there. So you're right ahead of it. This gives a family of lower bounds. Namely, this is how I get L of t theta less than L of theta. Because term by term, it's going to be less than or equal to. Now, it doesn't satisfy all our requirements because we have to make it tight. So how do we make it tight? That's the next piece. But right now, I have a way of going term by term from the likelihood function and getting lower bounds at a particular spot. And it'll be a lower bound no matter where I am. But I have to pick a certain Q to make this operational. That's the piece. So I have freedom to pick Q, but now I'm going to pick a very specific Q, and that's going to give me a lower bound, and that's going to allow me to get the curve. Go ahead.
Was stars isn't Q actually greater than 0?
Yeah. So I said I was going to ignore the support. We can imagine, just for the sake of this lecture, that it's strictly greater than 0, so I don't run into weird things about what I mean by divide by 0. Here, because I'm controlling the multiplication in ahead of time, like, it does make sense, but like, you're right to point that out. So just think about it as greater than 0. Yeah, wonderful question. Cool. All right. All right. So now how do we make it tight? So what we have to do, the intuition here is that we want to make Jensens inequality tight. And the idea is, if what's inside is constant, imagine there was a constant inside, that this term was constant for all the different values of z, then the expectation clearly doesn't matter, right? So if they were all the same, then these two would actually be equal to one another. Right? This is some value alpha, and then you would get a sum over all the alphas that were there. They would sum to 1, boom, done. if they all have the same value here, alpha, they would be here in the log, and they would also sum in the same exact way. So as long as this term is a constant, that is, it doesn't depend on z, I'm in business. All right? So what that means is I want to pick q such that log p of xz theta over qz equals c. Now before, I had all kinds of freedoms to pick whatever q I wanted. Now, this is where the probability comes in. So qz has to be related in some way to px of z for this to work. Oh, go ahead. What is z or c? Oh, c is some constant. This is a constant independent of the, just for some constant c. It does not depend on z. Independent of z. We don't care what its value is. We just care that it doesn't depend on z in any way. And then it will be exact equality. Then Jensens will be equality. Okay? All right. So what is the natural choice? Well, it's that qz should equal p of z given x theta. Why is that? Well, this is also equal to, so this is because p of x of z of theta equals p of z x theta, p of x theta. So if I plug these in, they cancel out. And c is equal to log px of theta. Okay? So let me make sure this is clear. Note, this just means note well, NB, I just use it reflexively, just to signal. QB does depend on theta and x. So we're going to have this notation qi of z because it depends on each different value. So each data point is going to get its own different q, which is the log of how likely this thing is. Okay? And we pick those for each I. So because we did this term by term, we can pick that q, q1, q2, q3, all different, and we pick them all so they satisfy this equation. Okay? This thing has a very famous name, so I'll write that while I was kind of stall for more questions. So what we've defined here, it's called the evidence-based lower bound, or the elbow, which actually is a fairly, like if you say elbow to a machine learning person, they actually know what it is. It's not something we're making up, it's a real thing. So the elbow of x, q, z equals the sum over z, qz, log pxz theta over qz. Okay? And what we've shown is that L theta is less than or equal to, or is greater than or equal to, the sum, because we did this term by term, of the elbow of x of I, q of I, theta. Sorry, this is incorrect notation. This is theta. Sorry, the z is marginalized away. The z can't appear there. Only theta appears there. Okay? For any qi, satisfying star. Sound good? That was just restating the lower bound. All I said is we went term by term through this thing, so it holds for every term that we can pick qi as long as it's a probability distribution. It's a lower bound. And then we also showed that L theta t equals sum I 1 to n elbow xi qi theta t for the choice of qi above. So hopefully that picture makes sense. Again, just to recap what's going on here. We have this opportunity to pick these bounds, and we'll use them in a second. So it'll hopefully become more clear exactly what we're kind of optimizing for here. What we're going to do is we'll see how we pick the QIs and all the rest in a second. But this is basically saying that it satisfies the two properties that we had before. We're going to pick where we are on the curve. We're going to find this kind of bowl shape, upside down bowl shaped thing. We're going to then optimize that thing in a second, pick our new theta t, and then repeat and do another curve that's present. All right, so let's do the wrap up and state the algorithm now with our newly hard-earned language. Yeah.
What is it like this low case level instead of the upper case level? Because like, isn't we redefining a lower bound?
Oh no, so these are both on the original loss. These are just saying this is the LT here, capital L. This is, each one of these is capital L basically, right? And then this one here is saying that at the particular point for that teeth instantiation, this is where we are. Yeah. All right, so the wrap up is as follows. This is what we can now write down the algorithm in the kind of full generality with mathematical precision, although it may still be a little bit opaque. We set Qi of z in the E step equal to the probability that Zi given Xi and theta, okay, for I equals 1 to n. Okay, so this says that you're going to pick the Qi distribution that says, what's the probability that's kind of, most informative, or the exact probability that comes from your model knowing the data and the current guess of your parameters, right? So you have some theta at some time, you plug it in, you know the data point that you're looking at, you condition on that, and you say, what are the most likely values of the cluster linkage, as we were talking about before, the source linkage for this particular point. You get a probability distribution over those, you set them to QIZ. That's really what's going on. It's your estimate of how likely that is. Then, you take an M step. Theta t plus 1 equals argmax over theta of LT theta, which equals, so LT theta, sorry, I'll write it like this. LT theta equals this elbow sum. Xi, theta, Qi, theta. Okay? Your current guess of parameters. So basically what it's saying is you give me a current guess of parameters, I get the lower bound that's underneath the covers, then I optimize that lower bound surrogate, I get the theta t plus 1, that gives me a new guess of parameters, which defines yet a new curve, a Qi for each one of what's going on, then I go back. Yeah, please. Oh, sorry, yeah, good call. Yeah, this is Qi, and this is theta, and I'm inconsistent with the semicolons too. So you move this, so there's a good bit of distance. This is an x, this is a q, this is a theta. Awesome. Please.
A small rotation question. I guess t is the iteration number in the training, right?
Right. Yeah. So it just as before. T starts at 0, we have that initial guess, and then we go from there. Theta is our current guess. Cool. All right. Why does this terminate? And it's basically for something that's kind of not very interesting or satisfying, but it does. This gives you a sequence that is monotonically increasing or non-decreasing. Okay? So it's possible that it would grind to a halt, but eventually, it has to be strict. There are some other things about how fast it terminates, but it's not. It's a monotone sequence, so we'll have a convergent subsequence. It's really all that matters. Okay? We don't say how fast it converges. It's a separate issue. Is it globally optimal? Well, no. No, just look at the picture. And so to derive a counterexample, you would just find a likelihood function that had those two bumps, and you would run it in that particular lower bound setting. And what it will do is it will gradually hill climb. And this is actually not great. It can't go back downhill, right? It's got to just continue to go up. If it gets locked inside one of those bumps, it's kind of toast. Okay. So in summary, what we saw here is we derived EM as MLE, okay, as promised. Okay? So just to recap what happened here, we started with this notion around Jensens and convexity. So we looked at the pictures of convexity and we got an intuition of what sets are convex and which sets are not. We wanted to use concave functions, which are these kind of downward facing things. The chords are always below them, okay? Those are the loss functions because we wanted to maximize them. The reason that was important is we had to do this back and forth iteration. Given a set of parameters, we were going to find a surrogate. That surrogate was going to be concave in our setting. It's going to be one of those nice functions that we were after. We would use Jensens inequality as a way of constructing that entire curve. We needed the entire curve because we wanted to optimize it. So it wasn't enough to find a point in a lower bound. We needed to find the whole thing that was underneath it so we could run our argmax step. And that was the setting where we would learn all of the parameters and estimate that in a way that was hopefully nice and easy to do, right? Which was like, you know, estimate the means and the variance of the data that we're given. Okay? We'll run through an example of that. This is a necessarily kind of abstract and confusing algorithm. The best way to understand it is just to run it through a couple of the different examples, EM and the next one factor analysis. And by the end, you'll be like, oh, okay, that makes sense. It's a lot of notation because we're abstracting out a huge number of things that we're doing. Okay? But in the end, it's not so bad, right? You take the QIs in this way, set the thetas, do descent on them, or ascent in this case. Do argmax. Okay. All right, so let's see it for our Gaussian mixture model. Okay, please.
Could you explain this termination condition a bit?
Oh, so the termination condition is not really important or in the classical sense. The thing is that it's non-decreasing, so that like eventually there's a convergent subsequence of it. I'm not telling you how fast it converges, for example. And it converges for the same reasons that GMMs converge, that we were like kind of going downhill, if you remember at every time. Like there was some loss functional that was decreasing. And this is just saying there's something that's continually increasing. When do you terminate it operationally? Like you're running this algorithm, when do you decide? You look and see if the likelihood function is not changing too much. What does too much depend on? Depends on your data, depends on the problem. Like sometimes 0.1 is good enough if you have a huge amount of data and you're averaging over billions of examples. Sometimes if you have only a small amount of data, you want to get to like machine precision and 10 to the minus 16. And so that's the way you decide when to do it. This just says that it's not going to oscillate wildly. It's a very weak statement I'm making. Yeah. Please.
Can you explain like what specific part of this is linked to the MLE sort of aspect of it?
Oh, awesome. Yeah, so we're going to see the MLE when we actually do the computation here. The reason it's linked to MLE comes from a very simple piece, which is we started in this model where we were saying the way we're going to think about the world was to maximize the likelihood, and that was like how we think about our data. That's less disturbing to this group than it is to like, I guess, generally worldwide who think about this, because like this is the only framework we've used in the course, but that's what I mean. We started with L theta as what we were optimizing, and then we derived this as a set of concerns. We didn't get to a global optimum, so I don't mean that like we definitely guaranteed that we got the maximum likelihood estimation, just that you can phrase what's going on as MLE, and so when you get into other estimation problems and the sub-problems, you just apply the MLE stuff you learned from the first half of the class, and we'll see that in an example. Does that make sense? Awesome, thank you for the question. Please. Which one?
Why is it hard? The MOU constructed?
Oh, it's tight because we went through this small piece here, which was that if we selected it as a constant in this particular way, so before we could pick any Q and it was a lower bound, as long as we did this, then actually this line was no longer an inequality, but was actually exact equality. And it depended, though, that selection of Q depends on theta and X. Awesome, great question. Yeah, and that's just making sure that the picture in your head is exactly right. We go up to the loss curve, we get something that's underneath it that touches at that one point, and then any optimization we do there is actually also optimization on the loss curve itself. Cool. All right. EM for mixtures of Gaussians, or we call them GMM, sorry. All right. All right, so what's the E step? Yeah, I'm just going to copy down the thing because we'll just get the generic algorithm. So let me get the generic algorithm. All right, just so we have it on the screen. So here's our warm-up. Not really a warm-up because we're almost out of time. But here's, remember if we saw how this worked. Px, yi, and zi. Remember we factored it as the following. This is just Bayes' rule. Nothing crafty going on here. Not tricky. Zi was a multinomial. Okay, this means phi I greater than 0, sum phi I equals 1. Okay, and this was, remember, our in cluster J. And so then once we knew, given Zi equals J, then every cluster had a different shape. So we had a different mean, mu J, and a different size or variance, mu J. And I'm doing everything in one dimension, but in 2 dimensions you would have actually the whole covariance would be different. These are the cluster size descriptions, cluster means. Okay? All right? Zi is our latent variable. All right. So let's take a look. What does EM actually do here? Okay. So what is EM? EM is very general. You can instantiate it, right? So what does it mean here? So Q I of Z is going to be equal to P Zi equals J given Xi and so forth. Okay? Now, what actually happened here when we wanted to understand what was the probability? This says the probability that I, the ith component, belongs in J, given what we've observed about Xi and what we know about the cluster shapes and their frequencies. Okay? So if you remember, we had this diagram that I drew quite poorly the last time that said we had these 2 bumps, which were our 2 Gaussians, let's say, in 1 dimension, that look like this. This was mu2, sigma 2 square. This was mu1, sigma 1 square. And the question is, you give me a point here. This is my xi. How likely is it to belong to 1 or 2? Cluster 1 or 2? Right? That's basically what we're asking. What's the probability that this point, this ith point here, comes from 1 or 2? Now remember, if we just looked at this, and these points and these 2 distributions were the phi's were equal, that is, both sources were generating the same amount of information, then we would say, oh, it's probably much more likely it belongs to this function, cluster 1, than cluster 2. But if we knew, say, on the other hand, if we knew phi 2 was hugely bigger than phi 1, right? 1 billion points came from the second source, and only 1 point came from the first source. We'd probably say that it's more likely that it would go to this, right? It would certainly boost its probability. So now the question is, how do we automate that reasoning? And that is Bayes' rule. More likely than 2. So to automate this is Bayes' rule. This is all we did last time. Bayes' rule. It just weighs those 2 probabilities and tells us what should happen. That's it. Okay? We ran through exactly those calculations last time. All right. Let's take a look at the M step now. In the M step, we have to compute derivatives. I want to highlight only one thing here because it's something that causes people pain when they do their homeworks. We have to compute derivatives. So we're maximizing here over all the parameters, phi and mu and sigma. Sigma is, all the covariances. So these are the sigmas, lowercase. In the notation above, these are all theta, or all theta, right? So theta refers to all the parameters of the problem. We were breaking it out into mu's and sigmas and phi's. Those are all the things we were observing. Everything that's non-latent, that's observed, not hidden to us. And what we were maximizing over from our elbow lower bound was this. Sum over zi, qi zi, log px of I, zi, theta over qi of zi. Okay? This whole thing, we're going to call it fi. This is fi of theta. Okay, hides a ton in our notation. All right? So this thing let's write it out, because the gory details will help us. Oh, please, there's a question. Yeah, so in our terminology, Z is just latent. So I'm giving you the intuition that it's something that's hidden or not observed. But formally, it's just going to be anything that's a Z. Z is latent. That's our definition. Yeah, please.
So the FI just the elbow that we got.
Exactly right. Yeah, this is exactly the instantiation of what we had above. We reasoned about this through ad hoc reasons last time, but it is exactly the elbow that we're now going to minimize with derivatives. And to make it concrete, I am either going to waste a bunch of your time or something will snap in your head and see how these things put together. I'm going to write out exactly what fi theta is so that you can see like what the derivatives are that you will compute on this thing. Because right now it's probably pretty mysterious to you. Like there's elbows and there's p's and there's q's, and like you can just write this thing down and compute its derivatives, and that's what you do. I mean, that's how this whole method works. Just abstracted it like 3 orders of magnitude more than it should be. Okay? So let's see that piece. Oh, please.
The zi that we're summing over.
Yeah, that's going to be, so I'm just using that notation to make sure it's clear that it depends on the I. It's actually just a z that you're summing over. And it's summing over, for example, like we're imagining that it's discrete to make our notation a little bit nicer. It would be summing over all of the different clusters that are possible there, all the different sources. How likely are you to be in cluster 1, 2, 3, 4, 5, so on. You could also, we'll see later, replace it with an integral if you had something really fancy that was there. Like if you had a continuous distribution over the hidden states. Yeah.
The way we define Z, it's very similar to what phi does, right? If phi is greater than, phi1, phi is greater than phi, the probability of from one source is larger.
Yeah. So it is, in fact, because of this right here, which I kind of glossed over, Qi is exactly setting this function. So I glossed over this really, really quickly because it was the same calculation we did last time. Pzij, to compute that, we expanded it by Bayes' rule. We had 2 different components. We had, if you knew you were in a cluster, how likely is the data point? And then we had a term that said, how likely is the cluster? And those were the 2 functions that we put in and broke down by Bayes' rule. It's exactly the same. You got it perfectly. So let me write out this monstrosity, just because it'll be potentially, it has been in the past educational. Who knows if it's educational in the future? And the future being like 2 seconds from now. All right, I'm going to use a notation, and hopefully it doesn't confuse you. Qi equals zj, so this is the piece there. So this is the weight. This wi is the same wi we had before. I'm sure you're intimately familiar with all the notation I use in the GMM lecture, but it's the same wij that we had before. It's the weight that summarizes this probability, just so I don't have to write that whole thing out. Okay? All right, so fi of theta is going to be equal to the sum over j, because now I'm summing over the cluster centers, right? The zi notation was still very abstract. wji, which was summing over this part here, log, and help us all, 1 over 2 pi, this is the covariance 1/2, this is the exp of 1/2 xi mu j square. Oh, I decided to write this in for general things. Why do I care about that? Oh, I see why. Okay. Transpose sigma inverse xi mu j times phi j. Oh, I just missed it. Oh, that hurts. All right, let me scoot. So much better here on a whiteboard. That's really catastrophic. phi j. Okay, let me make sure the brackets are clear. I'm going to highlight the brackets like it's a syntax editor. So make sure they're all there where they're supposed to be. This blue goes with that one, so on. Okay, great. And that means I'm missing a log. Perfect. All right. Not so bad. Oh, and this whole thing is, unfortunately, snap to, yeah, over wij. Right? That's just this piece is this piece. This piece here. This is the probability. This is the Gaussian, remember from our model? Let's go back up here. Sorry for all the scrolling. This is our Gaussian here. This is the Gaussian distribution with center J. I did use a higher dimensional covariance because it's something you're going to have to compute. So I've gone from 1D to higher dimensions. The notation doesn't change except for this is what the Gaussian looks like instead of a square. You know that already. And then there's the phi j, which is just multiplied times this horrible expression. And this x parentheses is so I don't have to write it in superscript. Right? Just exp of the function. Just a bad habit that I always use brackets for this. It's historical, and I would love to beat it out of myself if it were possible. Please. Right now, the covariance does not depend on z. In our model, the covariance here is something it depends on which cluster. Right? So it depends on J. Sorry, I just want to make sure I understand what you meant. Yeah, so I think if it means it depends on J, yes, the covariance could have different shapes. Some could be long and skinny, some could be short and round. Yeah, those depend on J. So this thing here is a very polite way of saying this guy here should depend on J. Yeah, good catch. All right, so now we can compute some fun derivatives, okay? So let's compute mu j of fi of theta, okay? We have to estimate the mean, right? Now, and I'm going to do something slightly harder. So apologies if you wrote that down. Let's do this. It'll be just one extra line because it's all linear. I'm going to sum over all the data, 1 to n, okay? So what this becomes is I sum equals 1 to n. This is over all the data. I get mu j here, mu j, times, and then it's going to be wj, and I'm going to drop terms inside the log that obviously have nothing to do with mu j. 1 half x mu j I, t sigma inverse j, x I mu j. All right. And so just so you're clear what's going on here, the log turns these multiplications into additions. So when I take derivatives, like this doesn't show up anywhere because sigma doesn't depend on it. And it doesn't depend on mu. And this doesn't depend on mu either, so I'm left with these terms. Please, go ahead.
Oh, like what is the physical meaning of fi here?
Fi is just the term here in the function. It is the likelihood function after we've picked q at the particular iteration. So it's just notation, so I don't have to write this monstrosity every time.
Yeah, but like here is like.
It's the elbow.
Okay.
It is exactly the elbow. It's the fi is the ith elbow.
Okay.
So why WJ has something to do with you?
Actually, it doesn't. I don't know why I kept it. Yeah, WJ doesn't have anything to do with lambda j, so it should be crossed out. Is that true? Let me make sure I'm not mixing something crazy here. No, it shouldn't have anything to do with it. But it will be sorry, all right, I see what's going on. This is what's going on. This is 1/2 and this is a minus. Wij is multiplied by it. Wij is, take the derivative of the log, it's going to be this times this thing plus. Yeah, sorry. Thank you for the notational issue. Yeah. Cool. All right, we're in business. So what happens now? Well, some mechanics that almost certainly will introduce bugs and you will catch and it'll be great. That's learning happening there and me making mistakes. Okay, so when we actually compute this is going to be sigma j xi minus mu j. You've computed this a bunch of times, all right? So yeah, all good. So when can we pull this thing out that's repeated? Because it's full rank, we can pull it out and it's linear and it doesn't change anything. So We want to set this to 0 and use that sigma j inverse, sigma j is full rank. And that will become clear in a second why that matters so much. Because when we pull it out, what do we get? We get here sigma j inverse times sum, which is an unfortunate collision, I equals 1 to n, wij xi minus mu j equals 0, okay? But then, because this is full rank, the only way that this thing is 0 is if it's identically 0, right? If this were non-full rank, sorry, the j is in the wrong spot. That's extraordinarily confusing. If this matrix, since this matrix is full rank, for this thing to be 0 means that this blue part is identically 0. And so what that tells us is mu j should be equal to sum I wij xi over sum wij. Yeah, as before. Okay? So far nothing happened. We estimated the means by simply averaging their weighted averages, and we computed this before, and it's just a matter of computing the derivatives. The one that I actually care about showing you, by the way, is phi j. So let me just jump to that, because we only have a minute or two left. And I want to show you what happens in phi j. So phi j is constrained. Please.
Would you mind showing me what screwing it up?
Sure.
Yeah, like, I just want the math.
Okay, sure. Also, I would say, ahead of time, I do post all the notes online. Please feel free to take a reference to those notes too. They will have potentially fewer typos than me trying to answer questions, draw, and generally be distracted. Can't focus that long. I have to read them many times. They still do have typos though, so always look at the notes. All right, let me just show this one thing. Phi j is constrained. Okay, so phi j is constrained, and I just want to remind you of something that you probably learned in high school or like freshman year in calculus. I don't actually know when anyone learns anything. Anytime I say something like that, my students always get upset with me, so I should just stop. But I assume you've seen it before this moment. How about that? You need a Lagrangian. Okay? No, you haven't seen it? That's fine too. I will post, if you want, I'll post notes about how to compute Lagrangians as well. If you haven't seen this before, this will trip you up in some way. So when you compute the derivative with respect to phi j, what happens is you're going to get something that says you have this weighted sum wij times the derivative of phi j log phi j plus, so if you just take this and compute the derivative, it doesn't account for the constraint. Okay, so you have a bunch of numbers that must sum to 1. So if you think about you're on a line, let's say that you're optimizing on a line, right? If the gradient, like let's say that your points are on this line, and you're saying like I want to optimize here. This condition that you could imagine for an optimal solution is the gradient's identically 0, right? That vanishes. That's good, that's a point. But what if the gradient is perpendicular to the line? Like it wants to push you only perpendicular and has no component moving you along the line, right? In that case, this is still a critical point. It's still potentially a minimum. Does that make sense? Because it's not telling you that there's a minimum to your left and right. It's, or along the line. Okay? So the question is, how do you encode that information that you want to kind of screen off information that's orthogonal to the line? And I'll write up a little note to show this whole thing. What you do is you introduce this thing called Lagrange multipliers. And Lagrange multipliers, and if you haven't seen them, don't worry. These are super easy to teach. Just say this. It's just an extra term here. And this multiplier, it's not obvious in this formulation what it's doing, but this multiplier is basically the thing that's screening off things that are orthogonal to these constraints. Okay, so this constraint here says theta j is equal to 1, and you set this constraint equal to 0, this term equal to 0, and it says if you're going off in a direction that would not change any of their values, that's okay. You get to screen that off. And I'll make that geometric intuition. I'll just post a one-page write-up for you. Please remind me in the thread, and I will definitely do that. If you don't do that, you'll get the wrong answer. That's also a motivation to learn it. And so what ends up happening here is you get something that says, I get sum I goes from 1 to n, wij over phi of j plus lambda equals 0. And this implies that phi of j is equal to 1 over lambda sum I equals 1 to n of wij. Okay? And the lambda is playing a very simple role here. It's just telling you, like, you have to normalize them in some way, right? Now, since, in this case, we can do it in an ad hoc way. Since phi j is equal to 1, this implies the sum of phi j is equal to negative 1 over lambda sum ij wij, and this equals negative n over lambda. Okay, and that's the correct normalization, right? Oh, sorry, this is equal to negative n. Oh, sorry, n over lambda, right? And so now you can then go back and normalize and cancel out divide everything by 1, since this is just, this sum is equal to 1. I divide everything by 1 here, and that tells me that lambda must be equal to, 1 over negative n. Right? This is equal to 1. So this implies lambda equals negative 1 by n. It's just normalizing. It's just doing the average, which was weird to look at before, but that allows us to compute all the things in the way we'd expect. Here it's totally natural. So if you don't get the general rule that I'm trying to tell you, the reason I'm trying to tell you is I think we make you use it at some point, this rule. So just check, it'll come up on a homework. I don't think it comes on an exam. But just flag something when you have a constraint. When you have a constrained probability distribution, you have to use a Lagrange multiplier. That's all I care about that you understand. In this case, it makes total sense though, because these numbers have to sum to 1. So if you don't have a normalization constant here, you're adding up a bunch of numbers which individually sum up to n, right? The sum over all of them is n. You better normalize them in some way. And this is just the principle that tells you you have to normalize them by this n factor. Okay? So all I care that you take away, if you've seen this 1,000 times before, don't worry. I hope you had a nice rest. If you've never seen this before, I just want to flag for you, when you minimize a function that's constrained, make sure you use Lagrange multipliers. I will put up a little tutorial about them. You do not need to spend a bunch of time on them. It's just if you see some challenge where you're actually supposed to, some problem where you're supposed to do it, just have a little light bulb that goes off and says, okay, I got to look up how to do it in this case. That's all I care about. Okay? And you'll trace through it in the notes, please.
The question really right minus n over lambda equals to 1, because that is lambda equals to minus.
Yeah, it equals to equals minus 1 over n, because there's a negative sign everywhere. So this minus lambda is going to be equal to 1 by n. So I'm just going to write the final expression. Maybe that will be less. Yeah.
So, that carries on.
Oh, sorry. Oh, this arithmetic is what's bothering you. Sorry. This is true. Yeah. Sorry. I just swapped them, and even that's backwards from how it should be written. I didn't see that. Sorry about that. Thank you for the catch. Right? It's just supposed to average out, so it looks the same. Awesome. Any questions about this? All right.
So, also, why phi j equals to 1?
Because it's a probability distribution. So again, the issue here is phi j is constrained by the model. So if we go back to this model, this is a constraint on phi j. So whenever you have a probability distribution, a multinomial probability distribution, it's not just that the phi i's are non-negative, which is a constraint we're almost ignoring, but is that the phi i's equal 1. And so you couldn't, for example, set your probabilities to be 0.5 and 0.8, right? They have to add up to 1 here because it's a multinomial. So when we do the optimization, we could, for example, prefer an optimization where we make all the probabilities 1, but that would be an invalid setting. And so that means these phi j's, we have constrained them to equal to 1. So now the question is, when we do the gradient descent, which is exactly the gradient descent we did before, where does that show up? And it shows up in this extra term here, which is the Lagrange multiplier. This thing is called a Lagrange multiplier. The multiplier itself is called that. Okay? And this is the constraint put into the normal form. If you haven't seen this before, it'll look quite mysterious. But what I was trying to do is, I'm not going to teach you Lagrange multipliers in this class. I'll put up something. But the piece is here that it gets you back to an expression which makes sense in this setting. And you needed something to average over, because these numbers sum up to something that looks like n. If you just compute it naively, you'll get something that doesn't make any sense. Yeah, please.
I think the problem is that in the line, since phi j equals 1, then you're missing a sigma in front of phi j.
No, there's no sigmoid here.
A sigma, like for summation.
No, in this setting, the sigma's out here.
Yeah, but like the other one, like since pj equals 1.
I think what's confusing you maybe is this, that these are not the same j's.
No, like that's
Which line?
since pj.
Oh, I see. Sorry. Yeah, I was talking while I was saying. Thank you for the clarification. That was really helpful. Apologies for that. Yes, it's this constraint here. Sorry, this is the constraint that was in our head. Yeah, and it just makes a mysterious reappearance here. All right, awesome. Okay, so what is the message that I want you to take away from this? Two things. First message is GMM is an EM algorithm. Okay? That's really, one of the pieces that is there. And this is interesting because we're going to see in the next lecture, we're going to see a different example, which is called factor analysis, where Z has a very different form, and it's meant to constrain the problem in a different way. We went through in this lecture a couple of different steps. We started with that convexity piece so we could get an intuition for what these functions look like. We didn't want to use convexity, we used concavity. And then we went through the EM algorithm, which we formalized as kind of back and forth with using these curves over time. Once we had those curves, what was happening was we would pick and optimize on those curves, and we were getting these QIs, right? The QIs played a starring role. Those became our W's here, and they kind of add nastiness to all of the equations, but not a tremendous amount of nastiness, right? They just add little weights and expectations everywhere. And then we ran exactly the kind of standard supervised machine learning, if you like, or the stuff that you've been doing for MLE for the entire quarter on those properties. Then we introduced a ton of typos to keep you on your toes. No, I introduced a ton of typos because I was talking while I was writing, and I shouldn't have done that. And so then we saw the two things that I cared about you highlight. One is you know how to find means, and these are just weighted means, and you should run through that calculation to make sure you know how to do it, because I'm almost positive we will ask you to do it at some point in the near future. And then the second thing that I would tell you to do is when you have constraints, you have to know how to optimize them. You don't need to know the general theory of how you optimize against nonlinear constraints, but you should review how to do this when you have something that sums to 1. It's not more complicated than what I wrote here, but make sure independently you go through it and ask questions. I'm happy to ask questions. I'm happy to point you to different resources. In the next class, as I said, what we're going to see is this notion of factor analysis. And that is going to tell us how to apply EM to a different kind of setting, which at first glance will look like kind of impossible to do without a latent variable model. And it's a pretty interesting scenario. And I think that's all I want to say. Any last questions before we head out? I'll stick around for a couple minutes as usual. Thanks so much for your time and attention.